Now, a very simple way to track the rate of pozzolanic reaction is to simply compare the strengths of these materials. Okay. So, if you plot the relative strength, okay, let us say this is the graph for strength development of Portland cement or cement mortar, Portland cement mortar or Portland cement concrete. So, we know that at early ages there is a very quick reaction and this reaction slows down later, and then you start going in more or less a maximum strength will be reached and you will not really see major strength development after that. Now, a system with Portland cement and pozzolan, where partly the cement has been replaced by pozzolan. Of course, the replacement levels will vary for the different types of materials that we are considering here for this kind of for an assessment. The pozzolanic system, because of the slow rate of the reaction, you will start off a little bit slower as compared to the cement, but assuming you continue to cure, assuming continuous curing, you lead to a condition where the pozzolanic system exceeds the cementitious system in terms of the compressive strength. This is just in terms of relative strength. We can do this comparison with respect to other sorts of mechanical properties also, but this is just a comparison with respect to strength. So, if you define the age at which this overtaking of the cement strength happens as T effective, the values of T effective for the different compounds are presented in this table. So, Ricer's cash is generally quite highly reactive. So, this can happen within 1 day. Silica fume can happen within 1 or 2 days, but generally when we are talking like this, we are also talking about a certain percentage replacement of the cement by these materials. These normal T effective numbers are given for 5 to 10% Ricer's cash and silica fume, 5 to 10%, and for type C fly ash we are talking about 20 to 30%, type F fly ash also 20 to 30%, and slag 40 to 60%, right. The T effectives that I have given there are for specific percentage replacements. It is not true for everything. For instance, if you replace type F fly ash or low calcium fly ash as 50% of the cement, you are going to wait much longer for strength development. You are not going to get strength in like 14 to 28 days. What does this tell you? It tells you that the speed of the reaction, pozzolanic reaction, depends on the type of pozzolan. Silica fume and Ricer's cash being highly pozzolanic because of their high purity silica are able to react much faster, because of which they are able to substitute cement and still produce the same strength at 1 day. Whereas, if you use a high calcium fly ash, the strength development will be slowed down to some extent and you will probably get the strength only by 3 to 7 days. So, if you compare 1 day strength when cement is replaced by type C fly ash, it may not be as good as plain cement strength. But when you compare the 7-day strength, it is likely that you would have reached the same level of strength. Okay. Similarly, with type F fly ash or low calcium fly ash, before 14 days your fly ash system is going to lag your cement system significantly. But beyond that, by 28 days you will see that more or less the strengths have come out to be equal. That is all assuming you are continuously curing. You are not going to stop curing at 7 days like you do in the field. This is for an ideal scenario. And slag typically 3 to 7 days will be the time it takes to reach the level of a plain cement based mix. So, this again tells you very clearly that when you are substituting cement by any mineral additive, cure for a longer time. You need to cure for longer time. How long does the strength gain continue? See, theoretically the strength gain should never stop, because there is always internal moisture available which will continue to hydrate the system. But practically what happens is because of the barrier forming as a result of the hydrates, you do not have waste for water to get in easily, and then there is not enough space for your hydration products to form in your system. So, oftentimes the reactions in your system will not proceed to completion even if you cure continuously. Okay. But for early ages like up to 56 days or 90 days, the presence of curing is likely to keep on enhancing the reaction. But in the long term, you will certainly have lot of cement or lot of material that is unreacted. okay, because there is simply not enough space. The reaction becomes space limiting. We saw in the earlier discussion of cement chemistry that you are filling up the available space with hydration products, and these hydration products were a lot more voluminous as compared to the initial cement grains. So, once the space is not available, you do not have space for these products to grow. So, you are going to be constricting or restraining the extent of reaction that can further proceed. So, all reactions are usually limited because of the lack of space. Okay. So, even though I have depicted a seemingly continuous trend of strength gain, at some point it is not going to go beyond that. Okay. There is a lot of literature on that subject about how space becomes limited, and then you really do not get too much more enhancement in your mechanical properties or improvement in durability beyond a certain point of time. Okay. Yeah. Correct. Yeah, absolutely. So, for instance, if I am adding only about 10% of type F fly ash, I may not need to wait for 14 days or 28 days. My strength gain may be as similar as your Portland cement system. Yeah, so these are the effective times given for the typical dosage levels that we use. Okay. If you go to an RMC, when you have a fly ash based concrete, you will have fly ash typically at around 20 to 30%. If you choose PPC, Portland Pozzolanic cement, it is likely that your cement has about 30% fly ash. And slag cement is usually between 40 and 60% most of the time. There are cases where slag cements of more than 60% also are used. So, there you can imagine that you need to probably cure even longer. Okay. So, it is very important to understand this. Very often when you see people on sites, they really do not understand this concept well enough. They think that if cement is to be replaced by any other material, you can still continue your regular processes and get the same effect. The issue with mineral additives is because of this speed of reaction getting affected, you have to have a compensation by additional curing. But the amount of time and resources that you put in to do that additional curing will actually significantly enhance your long term service life, and that is where you need to put all your bets to ensure that you get a long term performance from your concrete rather than worrying about extending some periods of working in the short term. So, that is very important for us to understand. Okay. So, this is a very important concept because it tells you that for an early age strength, when you are designing concrete, let us say 28 days strength, okay, you will be limited by the extent of mineral additive that you can actually put in your system, right. Why do we talk about 28 day strength? What is the reason? Why do we want this 28 day strength? What is so significant about 28 days? Sorry? Yeah, I mean, the concept of 28 days came from 4 weeks or a month, close to a month. But in 28 days is a significant portion of the loading transferred to the concrete element. Does the concrete element need to bear all the loads that are going to come to it during the lifetime of the structure as early as 28 days? So, if I cast a beam, for instance, by the time the beam reaches 28 days, is it going to bear the load that it's going to bear throughout its lifetime? Yes or no? Have you thought about it? You construct a column, right? You are continuously constructing. How much load does the column bear while it is getting hardened? Huh? Mostly self weight, right? Maybe in 28 days, 2 additional floors may have been added, so it is bearing somewhat additional load. But in your building of 15 floors or 20 floors, 2 floors is not going to be a significant part of the loading. So, where is the need for this jumping to get this early strength? On sites, there is always a requirement to get the early strengths, and very often the reason why mineral admixtures do not get used to the extent that they should be is because of this over dependence on early strength for your construction projects. So, your strength or the load transfer is executed over a long period of time. You do not transfer too much stress onto the concrete early in its lifetime. So, you have some leeway in doing a design where concrete strengths can be considered to be at later ages like 56 days or 90 days, and that way you will be able to incorporate a lot more mineral additives in your system, and that obviously makes the system more sustainable. You are reducing cement clinker usage by substituting more and more with mineral additives. All this has to be carefully studied obviously, but there have been several examples where 50% fly ash, 60% fly ash has been used. Low calcium fly ash has been used as cement replacement, and still those concretes are surviving and doing well. That is because when they were constructing, the engineers saw that they could actually prolong the time of curing and wait for a strength at a later age, because there was no need to load the structure early enough. In this era of fast track projects, we often think that because we are speeding up the construction process, our requirement of loading or requirement of the full strength at 28 days is a must. Truly speaking, it is not. How much do you think is the maximum stress in the concrete as compared to its compressive strength in most conditions? How much maximum stress is taken by the concrete? You can always design with ultimate limit state, but what is the stress level you think happens in concrete based on the loads that are given? Because you have so many factors, even in the limit state design, you assume material factors, you assume load factors. So, very rare that your system will be getting loaded more than 50% or 60% max, very rare. This is in full service. So, during construction, you can imagine that you have much greater leeway in terms of allowing for a greater strength development. So, the reason, the very issue that leads to a slower reaction, Pozzolanic reaction being slower as compared to hydration reaction, that is the primary reason for Pozzolanic concrete having a lower heat of hydration, and that has its own advantages, less thermal cracking, right, better long term performance and so on. Unfortunately, because of that reason alone, that means because of the low rate of strength development alone, a lot of the initial phase trials with Pozzolanic cement were rejected by customers because they felt that the concrete was not getting strength fast enough, or the concrete strength was getting compromised because the cement is slower reacting. Now, what has to be understood in practice is that it is not the cement which is important, it is the concrete that needs to be designed for the strength. If you need a 28-day strength with the fly ash cement, you need to design it appropriately. You can't design with OPC, simply replace OPC with fly ash and then expect it to have the same behavior. It is not going to happen. So, when you are designing for strength, the cementitious content and water binder ratio that you need with plain OPC to produce a 28-day strength may be different as compared to the cementitious content and water binder ratio required for PPC. You may want a little bit higher cement and little lower water cement ratio with PPC to achieve the same strength at 28 days. Now, some years ago, instead of making the customer aware that it is the concrete they should be worrying about, not the cement, several cement companies went down the line of actually trying to make the Portland pozzolan cement start reacting faster and gaining strength as fast as OPC. So, what they started doing is crushing the PPC to much finer sizes, and they even came out with a brand name of PPC 53. You know that OPC 43, 53 are grades of OPC which relates to the strength attained by cement mortar at 28 days. So, PPC 53, actually if you look at the standard for PPC, it has to satisfy only 33 MPa at 28 days, because you want the benefit from its low heat of hydration. But here they started grinding the cement finer and making it react faster. They totally shot down the major advantage of low heat of hydration. Problem what happened with them is the bags they were using were similar to what they were using for OPC. So, when you grind the cement finer, the moisture effects are going to be more. So, you saw the cement was getting hardened in the bags very fast, very rapidly. So, life of cement was getting reduced because they were grinding it finer. So, even today some cement brands are available with PPC 53, but it really does not make any sense. So, one has to design the concrete to get the strength. It is not the cement strength that will dictate the concrete strength, unless of course you are working at the same level of cement content and water binder ratio. This is a concept which not many people understand. So, yeah, again this entire debate on the extent of mineral admixtures and its effectiveness in a cementitious system leads us to understand the need for determining very clearly the reactivity of the cementitious system. Okay. Now, there is a lot more literature available as compared to what I am going to present to you here, because this has been a subject of much research over the last 15 years. There is tons and tons of literature that has come out, but I have kept it at a fairly simple level because there is a lot more important aspects that we need to look at from the aspect of usage of these materials in concrete. But nevertheless, we will talk about some of the activity determination tests. The simplest way to determine the reactivity of a pozzolanic material is to simply substitute cement by this material and determine the strength of a cement mortar. You make a standard cement mortar, make another mortar where cement is replaced partially by the mineral additive, and then determine the strength. So, that is called the Pozzolanic Activity Index Test, PAI. Pozzolanic Activity Index Test, where Pozzolanic Activity Index is simply defined as the percentage strength of the pozzolan mixture as a function of the plain Portland cement mixture. Okay. Now, for different mineral additives, like for fly ash, ASTM defines the activity index test as per ASTM C311. For slag, it is C989, and for silica fume, it is C1240. There are some differences in these methods. I will let you read the standards and figure out what are the differences on your own. Okay. Now, one principal difference that I would like to point out here is that ASTM C311 and C989, they rely on producing mortar of the same consistency. So, water cement ratio is going to be variable. But when you use silica fume, if you try to do the same thing, because of the high water demand of silica fume, it may completely reduce the strength of your system. So, what the standard permits you is to allow a super plasticizer. So, you prepare the cementitious system, you prepare the system with cement and silica fume at the same water content, but with a super plasticizer to get the same flow. Okay. Flow is measured by a flow table test, which you typically do for cement mortars. So, that is the primary difference between the silica fume code and the other mineral additive codes, where super plasticizers are not actually permitted. Now, this is again very common issue that we see between the practices in India and the practices in Europe, for instance. So, strength of cement in India, 43, 53 and all that, how do you determine the water content for those strengths? Sorry? You determine it from the standard consistency. There is a formula that you need to apply, 0.85 times this thing. So, you determine the standard consistency and use that to determine the water to binder ratio required for your strength test to cast the cubes. Now, what happens is, because of this aspect, depending on the standard consistency of your cement, the amount of water that you add in your system is variable for different cements. Even for the same 53 grade cement, if there are different brands, each one of them may have a different consistency, the amount of water that you add will be different. As a result, the water to cement ratio of your mix is going to be different. If you go to Europe, the EN standard says that all mixes are to be prepared with a water cement ratio of 0.5. So, there they are comparing at a same water to cement ratio. Here we are comparing at the same consistency. Now, that produces a lot of different results, major differences in the results that you can expect from your strength tests. So, you can't compare the way that grading is done in India to the system of grading that is done in Europe. Okay, so, you need to be a bit careful when you look at the results and understand carefully what has been done. So, even in the Pozzolanic Activity Index test, there are ways in which you can look at the system either with more water to produce the same consistency, or with the same water content but with an added super plasticizer to produce the same consistency. Okay, so, you have to be careful about what is the system being adopted in the study that you are reading about. IS 1727, which is actually a specific standard applicable to pozzolanic materials, a lime reactivity test is specified. So, what does the name imply? Lime reactivity. Lime reactivity simply means you have a mineral admixture, you add lime and determine the strength that develops as a result of reaction of lime with the pozzolan. Okay. So, this basically is expressed, reactivity is expressed as the strength in megapascal. We will look at this a little bit later in more detail. Lime reactivity is simply expressed as the strength of the cement mortar prepared with by putting together a mixture of lime and the pozzolan. I will talk about the proportions later on, and then determining the strength, and the strength in MPa is the lime reactivity, not a percentage. Pozzolanic activity index test describes a percentage, or sometimes it is also simply called strength activity index test, strength activity index, SAI. Okay. There are other indirect methods. As I said, this is the subject of a lot of research. In fact, there are people who are going on developing new tests just from the point of view of being more relevant than the others, but you have to take everything with a pinch of salt and ensure that you understand what is going on in each of these tests. What are you actually measuring is very important to really understand. Now, strength activity, especially your lime reactivity tests, are not necessarily ideal. Now, why is that? Because in lime reactivity tests, you add the lime and the pozzolan, right, and then you expect it to form CSH. But this is not really reflecting your cement system. Why? You have alkalis, you have gypsum present in the cement, which are further going to contribute to the reactivity of your pozzolan. You are not capturing that in the lime reactivity test. And because of that, what happens is sometimes, not every time, but sometimes depending on the nature of your material, it may work out less in favor of the silica bearing systems. For instance, this is one work that was done by one of our students here, which showed that the lime reactivity of products available in the market, low calcium fly ash and silica fume, the lime reactivity was not up to the mark. That is very surprising. Usually you do not expect that. Okay. You expect that products available in the market will be having significantly high lime reactivity. So, but the same thing for type C fly ash and for slag, the lime reactivity obtained using the same lime reactivity test was significantly high and was able to meet the standard level. And that shows that it seems to favor the systems which already have a high amount of calcium present in them, but it does not reflect the reality of a cementitious system. Okay. So, there are alternative methodologies prescribed, but they are not as straightforward for standard QC labs. In typical QC labs, they are okay to do strength tests, right. Any QC lab will have cement strength test. So, same thing can be applied for pozzolanic strength tests also. Usually the lime reactivity test also needs an oven at 50 degrees Celsius to speed up the reaction, but that is not really a problem. Usually for QC labs, you may have ovens available for aggregate moisture determination and so on. So, that is not really an issue for QC labs, but when we talk about other reactivity tests, as I will show you, they are not as straightforward for QC labs. So, let us look at some of these tests. Of course, we already talked briefly about strength activity test, but we will take a look at the mixture design in just a minute. We also have the electrical conductivity determination by a direct activation with calcium hydroxide. There is a more chemical test called the Fretini test, and then of course the IS lime reactivity test, which is also a strength activity type of determination, and lime saturation tests. Let us look at these briefly, and most of the examples here are from the research work of a student of mine who worked on sugarcane bagasse ash. So, many of the data that are shown in the next few slides are from that work. So, you will see bagasse ash as the mineral additive in that case. Okay, what is bagasse? So, after you crush the sugarcane and extract the juice, the fibers that remain are called bagasse. Bagasse has a very good calorific value. So, they burn it for producing electricity or producing steam for your sugar mill and so on. But after they burn it, the ash that remains is dumped because it is of no use after that. So, but then it turns out it has good silica content in it, and that silica is what we are trying to use. Right. So, electrical conductivity method. So, here what you do is you blend the material with powdered calcium hydroxide. Okay. The pozzolanic material to calcium hydroxide ratio is 8:2 or 80 to 20% if you will. Okay. And you prepare then a mixture with different amounts of water, and what you are simply trying to do is measure the electrical conductivity of the system. Why will that help? Why will the measurement of electrical conductivity help? Initially, of course, the system is wet, so the conductivity will be high or low. It is going to be high. As the hydration products form, your conductivity will start getting lowered, right. So, usually the work was done by McCarter, who was one of the very well known research scientists working on electrical methods applied to concrete. So, here there are several regions in the conductivity curve that are seen. You have region 1, region 2, region 3 and region 4. Okay. Region 1 you see a slight loss in conductivity, but then in region 2 you have almost a steady conductivity value. That means the reaction is not really happening at a fast rate. Initially there is some reaction which reduces conductivity, but then your conductivity is almost steady. Stage 3 you have a major decline in conductivity. That means this is the stage at which a bulk of your reactivity is happening, and then stage 4 the reactivity slows down, more or less similar to what we see with our cement heat curve, calorimetric curve of cement, more or less similar to that. Okay. Now, here Pozzolanic index is defined as the maximum rate of change of conductivity over the time over which it happens into 10 to the power 4. So, this is expressed in Siemens per meter per square of hour. Okay. Now, this is only a definition, just simply taking into account this stage 3 where the pozzolanic activity is maximum. Okay. And using this they are able to define, of course, the pozzolanic activity of several different compounds that they have investigated, including microsilica or silica fume, slag, calcined shale, fly ash and metacholine. So, you have different results available here. As you can clearly see, for microsilica, the rate of change of conductivity in that zone 3 is the highest. That means you have the highest rate of reaction. Then it turns out it is for slag. Interestingly, for metacholine they seem to have a very slow reactivity. I do not know why, because they may not have used a very high reactivity metacholine in this case. Okay. So, what they are observing is very clearly you can distinguish the pozzolanic activity of the system by simply measuring the electrical conductivity of the system. So, you can measure electrical conductivity quite simply. You can put your material, freshly mixed material in a cubical container, and at two ends of the cube you put electrodes, okay, and then you can either do an AC based system or a DC based system. AC is preferred, again we will talk about that later. Alternating current is preferred, and then at a specific frequency you apply a voltage and then determine the current and conduct that to change that to conductivity value. Okay, again this is the same thing in words which I just talked about.